Yeah. I got a question for you. To what extent does the original Rishon guy talk about anything like this?
Well, and this is going to be interesting because the Rishon person, he comes from a totally different point of view. So
Oh, really?
he starts with the standard model. And so the
Okay.
standard model means that you have electrons um, and what they call quarks that are
Hmm.
contro- that are composing the proton. You probably know from school you have electrons and protons, right?
Yeah. Yeah.
And the electrons are considered to be have no in the standard model to be solid with no internal parts.
Okay.
Proton is considered to have three internal parts called quarks, and that's why they're more massive and have more energy. And
Okay.
so, and that's the standard model. Now, most scientists don't like the standard model because they don't want to have two different kinds of particles. They only want to have one kind of particle.
Oh.
So there's been because that's the way. So this man Harami, he came up with a possible way to generate the quarks and the electrons out of a new type of particle called rishons.
Ah.
And then you could generate both of them out of one kind of particle.
Okay.
He called them the T and V rishons, which are really, even though there's two of them, they're really just a single one particle. Because there's always twos. There's always this duality in physics where you have a, um, a charged and an uncharged partner, and those
Yeah.
are considered really just one thing. Like you have the neutron and the proton, and
Uh-huh.
the electron and the neutrino. You
Yeah.
have you have the U quark and the D quark. You always have these doublets, but the doublets are
Yeah.
really just two expressions of one thing. But
Uh-huh.
the duality is always there.
Yeah.
And so he came up with the T and the V, which are really just one Rishon expressing itself in two ways,
Mhm.
and showed that he could generate the quarks and the electrons and neutrinos out of those Rishons.
Yeah.
Now, but he did so he basically started with the particles that we have and then said, well, let me find a way I can break these up. But I am starting from just saying, I'm gonna start with nothing. I don't have the standard model. I'm gonna see if I can find the standard model by starting with just simple idea of how combinatorics work.
Okay.
So so I just said, okay, if you have any things and you're combining them, is there something about combinatorics itself that will generate the standard model?
Okay.
And then you're starting from first principles. And it
Yeah.
so happens that from starting from first principles, I generate the Rishons.
Ah. Okay.
So I don't have to make them up based on the standard model. I can just show that if you do any combinatorics itself will generate the T and V Rishons.
Ah.
And okay, so and here's where it is. I can show you. I'm gonna move this over.
That's good.
So basically, the T and V Rishons. If you look at, let me get a good place. Well, let's look at this. We'll look at the file. No, let me look. Look at. Let me see. You see, okay, you have a number, and then you have a number. You have a number of elements in a
Yeah.
set, and then below it, you have the next order of combinations you can make. So if I have five, just like right here, if I have five single elements, then I can make 10 order two, right?
Yeah.
And if I have 10 order two, then I can make 10 order three, and so forth,
Okay.
right? Well, what I speculated on, well, what if I say, because of what I know about physics, is that the bottom, well, in this case, the five elements are the T's, and the 10 are the V's.
Hmm.
So what if the new thing that I generate are always a potentiality, which the V's are, because the V's are usually massless and don't have any charge. And
Okay.
then the 5 usually has charge and they usually have mass. So I thought, what if I think of the 10 as potentiality, and the combinations made out of the 5, and that the V's are always this potentiality and the T's are always what is given. So I took and said, no, what if will it work if I think of the T's and B's like that?
Mm-hmm.
And well, once it turned out it did work. It worked exactly. And so basically after finding about his T's and B's, I had been doing this combinatoric stuff for a while.
Yeah. And you
Uh,
see, I just fitted exactly into the same process you were doing.
yeah, and I can show you. Let me go over here. You see that new window?
Right here. Yeah.
Yes. Okay, where I got T's and B's on the side.
Oh, okay. Yeah.
Okay, so now these numbers over on the side are really the same numbers that we were looking at over there. Like the 0 and the 1 are,
K and N.
yeah, the K and the N. No, not the K and the N. They're the, let me
Okay.
go back.
Okay.
They're like the K and the N, are down here in the gray.
Okay.
But as you build up these, as you go up this column right here, if you go up this column, you get a 1. And remember that 1 is the empty set. And then I go to let me go back up to 5. The 5 is the number of elements in the next setup, right?
Yeah.
So that is going to be the T, the number of elements in the next setup. And then the possible combinations of those elements is the V.
Which is 10 here.
Right. So it's not actually the 5 down here. It's the number up here in the column that's generated by the 5.
Okay.
So it's a little bit
it's
different.
the same
So it's
column.
not actually the N, it's actually this number of elements in the set that's generated by the N.
Yeah.
Follow that?
I think so. Yeah. So
So
you're saying that you have 5 elements, and that would be the T,
yeah, the T would
and
be
the
the 5
V would be
elements.
the possibilities, which is a number below. It's more of a potential, and there's 10 of them.
Right, exactly. Because that's potential. I can take the 5 elements and I'm saying I can combine those into 10 things. Well,
Yeah.
that's the potential and that I can make from the 5. And so that the actual extension of things is always the T element and the potential is always the V.
Okay.
Now, but I'm going to need, but we're talking about the actual T and V's in physics, we got to go back to the fundamental. So we go back over here to 1.
Okay.
And we see this 1 right here. What's over top of it is the 0.
Okay.
So in this case, I only have T and I have 0 of these, right? So 0 V's and only 1 T.
Okay.
Because I have 1 T. When I have 1 T, you get 0 V's, right?
Okay.
Okay. Now, let me go back to that picture. I'm going to show you how. So these numbers, so this is the T right here. That's 0 and 1. I mean, but look at it the other way. See how it has an S and a T up there on top?
You don't have your new screen up. The other screen's still here.
Oh, it's still showing up?
Yeah, I'm still not caught up screen wise. You're showing me the original screen. Yeah. Okay. Now we're on the same page.
Just took a while to show
Yeah.
up.
Sure. Go on. Yeah.
Okay, so right up here, I have ST.
Okay.
Well, think of that S as really V. I have VT.
Okay.
Okay. And so,
When
you
t is
said
equal
I
to
had a,
1, you said v was 0.
right, exactly.
Yeah.
So since this is 0, then in reality, I only have over here, I say it's only a t because there's no v's, right?
Yeah. Okay.
Now down the next, it turns out that, remember when you make, remember you're taking a combination of two. So you're
Yeah.
putting two things together to make the V, right?
Okay. Yeah.
So in reality, the V is always going to be designated one half of that, not
Okay.
one. Okay. So
Okay.
this V, I have a minus one half, which makes the V, but I have zero T's.
Okay.
Okay. Now, and so then I'll go down and I show what, like if I have a negative T, that'll be a 0 over minus 1. If I have a negative V, that'll be a 1/2 over 0. And so I go down and I generate all these possible T's and V's that he has generated. Actually, I generate some that he doesn't generate, which turns
Okay.
out to make my, which turns out in the end, I can do things in the standard model that he can't do. But you see, what I do is I start from combinatorics and I go back to the fundamental uh, elements
Yeah.
using zeros and ones and minus one half and zeros, and I generate the T's and V's. And this is going to be the coolest thing about this is that when I start putting these together and make particles,
Hmm.
they start generating the exact combinatoric values that they need to generate.
Wow.
Here's,
So it goes back into the combinatoric system.
right. But
Yeah.
in physics, the energy is actually, when you have particles, they actually do calculate the energy the same way. You have a certain number of particles, and you say how many combinations you can do, and then the number of combinations is multiplied times a constant of energy, and that's how they measure the energy.
Okay.
Um, and so it turns out that when I start doing this and putting these together, I get the exact right answers for like the electrons and the quarks and everything. It
Yeah.
turns out to all work out uh,
Wow.
by doing what they call vector addition of all of these.
Uh-huh.
And so starting with that, I began to see this possibility. And then I went and started taking the numbers out like I'm showing over here. And then I started just building these in. If you go over here, then I say rich, I got these Rishon groups.
Okay.
Now what I've done here is put some T's and B's together. I have a T, I have a T, and I put it with a V and an anti-V. And I see how those add up. Now, let me see. And you can see that if I add a T, a V, and an anti-V, it's really going to give me just the same thing I started with, right? A T.
A T, yeah.
Because the V and the anti-V negate one another, right?
Yeah.
But if I go down here and I start with this T prime and a V and a V, it's going to give me something different. And it turns out that what it gives me is a special Rishon that he doesn't have in his theory.
Okay.
In my theory, ends up solving some problems in the standard model that his can't.
Hmm.
And it turns out it just all works out. I mean, I even just recently figured out that some of the problems I was having, even just about a few days ago, it turns out that it's even more exact than I even had
Originally
known
thought.
up to now. It's
Yeah.
really quite what you can say is what I've done is I've created an accounting system where I can account for all of the properties in quanta of the standard model using these Rishons.
Okay.
And
So how did you generate the T prime?
okay, the T prime, we can go back over here and see it. It's over here.
Okay.
So here's the T prime. Now you can see that the T prime over here, hold up, no, that's the minus T prime, that's the T prime. See where I got
Yeah.
it at?
Yeah, you got 30.33.3. Okay,
the
these
two,
are different standard elements.
yeah, so let me tell you how this works. These numbers I got up here, Q, these designations Q, Z,
Yeah,
R, and F. Now
yeah,
those are directly from physics.
yeah.
Now the Q is actually the charge.
Okay,
Now this charge in physics has a certain relationship to these other numbers. And here's how it goes. You see that R and the F?
okay,
These are certain properties in physics. And it turns out that the R plus the F, I should write it down here. Let me write it down here.
okay.
The R plus the F you put it in a comma.
Okay.
You
Okay, it's coming now.
see it?
Yeah, it's coming
Okay,
up. It's a little slow.
divided by 2.
Should we call IZ then, huh?
Let me show you. Let me do it.
Yeah.
I got a, then the IZ plus that, taking all that together. Hold up.
Oh, should we call Q then, probably?
Take all of this together. I'll just put the Q over here because all
Okay.
that equals the Q.
Yeah. Okay.
So that's the formula. That's a formula from physics. Um,
And this is a standard element
yeah,
approach?
this is the standard formula for any particle. This will always be true, that formula
Huh.
in the
Pretty
standard physics.
relatively simple formula, huh?
Yeah. So for any formula, charge will be equal to this thing called IZ, which is called the isotopic spin, plus
Okay.
R, which is considered, I call it, it means the Rishon number. This Rishon number turns into other numbers like the electron number or the quark number, plus
Okay.
F, which is called the flavor or the generation of the particle, divided by 2, will always equal the charge.
Okay.
And
Wow.
that's a general formula they use to describe every particle, whether it's electron or whatever. If I go do an electron, I can describe an electron the exact same way. For any particle, for any two particles, these numbers must be different.
Okay. That's the
Um,
distinguishing factor. They have to be unique.
right. So my numbers for T have to be unique, and all these have to be unique. So if you
Yeah.
look at my T prime, then you can see that the charge is the same as for the T, right?
Yeah.
But the IZ is different.
Yeah.
And then you also have these Rishon and flavor numbers are different too.
Yeah.
So even though over here you end up with the same combinatoric
Yeah.
value, it generates the same combinatoric value. If you look at all these, you'll find out that the combinatoric value is always 1 or -1 for all of these.
Yeah. Okay.
So
Yeah.
particles, it's always for any particle. No, it's not really true. For any particle, well, say it will. If most particles, it'll be +1, and well, it's not really true. I'm saying that, so I'm gonna say that. But anyway, it's going to be. Here's how you figure out the combinatoric value. You multiply the S by 2, you add it to the T, and you take the square root of it. So for this T, 2 times 0 is 0, plus 1 is 1, and so the combinatoric value of T is the square root of 1, which is 1, right?
Yeah.
And if I go down here and take the minus, if I multiply 2 times -1/2, I get -1, right?
Right.
Plus 0, then I get -1. And so V is equal to the square root of -1.
0.
The square root of -1 is a number.
Oh, it is. Okay.
And then the anti-V, the negative V, will be the square root of 1. But anyway, it'll either be the square root of -1 or the square root of 1. But when I start putting these together to make electrons and quarks, that combinatoric value changes, but it changes exactly the way it's supposed to change.
Yeah.
And I end up with, when I add these together, I get the exact right numbers for this Q, these IZs and RFs for the numbers that it's already given. So when I put my things together to form an electron, then I get the exact numbers that are already been found to be true.
Yeah. Proven. Yeah.
So, and it turns out that, and I even can account for some things that they can account for now, which has, what I'm not going to try to explain it all now, but it turns out, I mean, it's really, really elegant. It blows my mind sometimes that it even works.
This is like the guy that discovered the element. What was it? The chemistry, the elementary, the table of elements.
Oh yeah, the periodic table. Yeah.
Yeah. It sounds very similar. Like all of a sudden, you just woke up and sat right in the mind.
Exactly. It is what it's like. Because really, what I'm doing, see what, in a way, that's a good analogy. Because what I'm doing is really an accounting system. I'm showing how the quanta for all of the particles can be accounted to by just starting with these simple combinatorics representing T's and B's. Then I can generate all of the known quanta in association with the particles and the properties of them. And it's more of that because I'm not really doing the physics, the interactive physics of the particles, which has to do with how much energy and mass there is. I'm only talking about the properties and the quanta. But anyone who knows that, if I get all this written up properly, should be able to look at this and see the math that goes with it for the actual mass and energy. See, I'm not computing the mass and energy, but I'm computing what they call the factors of the mass and energy.
So it's almost like a precondition?
Right. It basically shows you whatever the actual mass and energy is, it's going to come in multiples. I'm sharing what the multiples are.
Yeah, the fundamentals that build up that.
Right.
Okay.
And so let me go back to the thing. It's going to take yours a while. I switch you back to the spreadsheet with the thing. And so basically what happened here is I end up, and this is the other part, not only do I have all the regular quanta that's associated with charge, but I have this ideal, that I just shared about how the gravity and mass comes in that I told you about.
Yeah.
Because when you do this combinatorics, you end up generating what can be understood as the energy of the curvature of space-time, as well as the complex systems themselves.
Wow.
And so all of that's kind of there, it's just unfolds.
Yeah. So when that parts that creates curvature and gravity, the space curvature, space time, and then the gravity, is that like again the fundamental particles that you're building up that could generate that?
Right, exactly.
This what's remaining is all the particles that could be used to generate that part of reality.
So so here's the way to understand it. Now, if you think of these letters, as properties, right?
Okay.
And so here I got an element that has a C and B property, right?
Okay. Yep.
Now next to it, I have another element that has part of the same property as the other. So now they're a little bit connected by that C property, right?
Yep.
So in a way, they're not as different anymore. If I go back to here, where I have the A and the A and the B are totally different.
Yeah.
Right. And that's why when we make combinations at this level, they will equal the exact number of elements that they create on the next level.
Yeah.
But here you end up having things which aren't really as distinguished as they should be. The Ca and Cb are similar. So the energy between them is less.
Uh-huh.
Follow that?
Yep, yeah. There's a less difference.
Right. And it turns out when you start doing the combinatoric values of these things, it bears out.
Okay.
Well, the energy now, what you're saying, the energy of the difference has went into curving the space
Mm,
between the objects. So now the objects themselves aren't as distinguishable.
okay.
And so what happens when you start making combinations of them, you can't make as many combinations, unique combinations, because they're very similar.
Yeah.
And at each level, they become more and more similar. So at each level, the system becomes more complex, space increases its curvature, but in a way, the objects are now closer and closer together and more dense
More dense. Yeah.
because they're more alike, you know. So things that are far apart in space in a way are very different from one another. As they start entering the combinations, they start moving closer and closer. It's the combinations actually which cause the motion between things. As they get real close, then you get this level of maximum combinations where they become undistinguishable from one another. And this is what I'm showing that is happening.
Yeah.
Basically, you end up in the end with the one where everything is now unified in this
Mhm.
one, the indistinguishable um, unity.
Yeah.
And that happens as you increase, at each level of combinatorics, because each at each level, the properties become more and more shared by the elements.
Hmm.
And that's sort of what is happening as mass gets built up and becomes more complex, and the space around the object becomes more and more curved. And so
Okay.
the reason it's curved is because I can talk about how that happens. You have well, just kind of complicated because you got to get into the whole thing of relativity, where gravity is actually the path that another object is following in the space that's curved by an object.
Okay.
Are you familiar with that?
No,
Uh,
but you're saying that gravity creates a path for another object to follow.
right, exactly.
Okay.
And the more, in a sense, the more internal dense an object is, the
Mhm.
less it interacts with objects outside of it. So its inertial mass increases, and its potential gravitational mass increases. Well, it's a little complicated, but
It sounds right. Sounds like Jada's photo.
right, exactly. And
Yeah,
so
because as
this,
it gets more intense, it has more energy, but it's inertia.
yeah, exactly, becomes
Different
more
type of energy. Yeah.
right. It has more and more mass. So in a way, its gravitational energy is more, but it also has more inertia. It's like a regular object. The heavier
Yeah.
the object it is, the harder it is to push.
Yeah.
But the heavier an object it is, also the greater its gravitational potential attraction.
Hmm.
And those two things happen at the same time. Inertial mass and gravitational mass increase proportionately.
Hmm.
And so
Okay.
this is what this is showing is happening, by this process of these
Yeah.
properties getting. And so all of that is just philosophy, though. But I
No,
think, I
but
think it's convincing. You
yeah,
know,
but it makes sense out of it in the sense that it gives you a bigger picture of it. You can kind of grasp it. Yeah.
and then what you have to do now. This example goes back. You have to go back to, okay. Well, this is all. I'm starting with five. The universe
Yeah.
doesn't start with five. It starts with one. Single elements. That's why
Yeah.
you go back over here to the page and you start generating the fundamentals and
Oh,
showing how the fundamentals can build up, into those complex systems.
yeah.
And that's what I do. I mean, with these things, I can generate all the electrons, the protons, the neutrons. I mean, all I can show why there's only matter and no antimatter. There's all the forces, the weak force, the strong force, the electromagnetic force. All of those are well described by putting together rishons in certain ways.
Yeah. But you said you increased the amount of reshots because you
Right,
developed more combinations that he didn't have.
right.
Yeah.
Let me see if if I can share. Of course I've made all of these into graphics, which I've shown you before.
Yeah. The theme where you can show all the different colors.
Right, and then I can put them all into
Yeah.
combinations and make it really clear.
Combinations. Yeah.
Um, let me see. I'm gonna stop sharing for a moment,
Okay.
and I'm going to share a different screen. Now you see in the Wishine element screen.
Yep.
Okay. Then of
Mhm.
course I showed you before. This is where I actually just show exactly how the combinatorics generates the Rishons.
Okay.
Like right here, I got I can generate. This is the V and T thing. Like I said, you can't
Okay.
see the arrow, can you?
Yes, I can. I can see the arrow on the
You see my,
zero.
my
Yeah.
arrow moving?
Yes, I can.
Okay, great. So this part over here is the V part, and this part over here is the T part.
Okay.
So I can like generate a 1/2. Um,
Combinations that you're showing on them tables.
right. And they will
Okay.
generate the associated particles.
Okay. So like if you look at this is the V at the end is the type of particle. Where would
Yeah,
you?
you see, if you look at this in reality, hold up, that's not the one I want. Let me see. Let
Okay.
me do let me do let me do it this way. Let me do 3 of them. Okay. So you see these are the V's. See these 3 V's
Oh
up
yeah.
there? Now,
Okay.
and I've generated 3 V's, so that 3/2 is 3 V's, right?
Okay. Yeah.
You know, um, let me clear that one. And then I can go change that, and I can generate 3 T's.
Okay.
Now then I can start making combinations of these.
Uh-huh.
Except I want to make a U quark. A U quark. Let me clear it. A U quark has a charge of 2, so I'm gonna go over here and I'm gonna make 2 because and
Okay.
then but it also has a V. A U quark is made up of 2 T's and a V.
Okay.
So I gotta go over here and I have to change it to a V. And
So
now see
okay.
1 T, 2 T's, and a V.
Okay.
And if you count the V's as 1/2, you'll see that these two are negative and positive, so they cancel, right?
Okay.
These two are negative and positive, so they cancel. So all I
Oh
have
yeah.
is -1, which is what I got here. -1/2, right?
Yeah.
And I have these two T's cancel. Then all I have is a T plus
Okay.
and a T plus, which is what I got here.
Okay.
And so here I'm showing the direct relationship between the Rishons and my combinatorics.
Works. Yeah.
That
Are
is
they just?
exactly that it exactly matches. So I actually came up with this part first, you know, and then I
Yeah.
decided, oh, maybe this part could be the V's and maybe this part can be the T's. And when I did it, I started being able to generate these things exactly.
Exactly. It's the same. All the reshots.
Right. I took
Wow.
be able to put the reshines together to generate the particles in the standard model. The particles in the standard models are the quarks and the electrons and all that stuff, you know. So I was able to do that. Um, and then I was able to do this. I'm gonna press this. So then the next step was to, okay, I'm gonna create these graphics to represent these T's and B's.
Okay.
And so now this is the graphic. Here's these two yellow things are T's.
Okay.
And above them, you would have the V's and the anti-V's canceling one another. And so these are all T's right here with the cones at the bottom.
Okay. And the
And
V's
then
are on
over
top.
here, when the cones are on top, they're V's. And these are my primes. These other things right here are primes.
Okay.
So I generated all the particles and made them into graphics. But not only did I do that, is I got all the quanta. See how up here where it says electric quanta?
Hmm.
So I can show there's the electric quanta, there's the isotopic spin, all those things I told you about.
Oh yeah.
There's the Rishon number, and this all changes when I click on these. There's the flavor,
Yep. Says it goes back to the standard format, and you're
right?
showing all
It
of this
shows
different.
all of the properties in the standard format for each one of these.
Yeah. Wow.
The weak charge, what is called the color charge, and what I call spin. These are all the quanta that are used to designate particles in the standard model.
Yeah.
And so what I do, I show when I start putting these in combinations, I generate the exact right quanta for
Hmm.
these particles from what I started with. So if I want to make an electron, I can do this, and I can click and get another one. And then I can get another one.
But you're picking particular ones for U quark, right?
I'm picking these T's to put them
Oh
together.
no, I see. It's changing every time you. Okay.
Yeah, and then I have an anti-electron I have made
You made
out of
it.
these quarks.
Yeah.
And if I go over here and I'll see that I could show that all the properties are correct. Then I have a 1 for the anti-electron, which is right for the charge. And all these other numbers are correct. The isotopic spin
Yeah.
is
Yeah.
correct. Everything is
Wow.
correct. The Rishon number, the flavor, the weak charge, the color charge, and the spin are all correct according to the standard model.